Assumptions in kinetic theory. Do you know your assumptions?
Uh, I think one of them is about the size of the molecules being much smaller than the size of the container.
Right? Good.
Another one is there are no intermolecular forces between each molecule.
Yep.
The time taken for a collision is much smaller than the time taken uh, between each collision.
Good.
And would another one be that they all follow Newtonian laws of motion?
It's not normally an assumption.
Maybe all the particles, all the molecules are the same size.
Again, not normally included in the list of assumptions. There's this one,
Oh, yeah, I forgot about that one.
and there's this one.
Oh, I forgot about that one as well.
Those are the five. Those are the normal five, and there are five. Most people would say there's five, and those are them. Okay, so you did pretty good.
Yes.
Okay, right. Then we've got a cylinder fitted with a pressure gauge. Right, so let's draw our cylinder with a pressure gauge. There is our pressure gauge. Doop, 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 doop. Right. Contains an ideal gas and it's stored in a cold room. Okay, so T is low. When the cylinder is moved into a warmer room, okay, over here, T is high. Um, the pressure of the gas is seen to increase. So this is explain in terms of kinetic theory why the increase in pressure is expected. So you've got to explain in terms of kinetic theory. So basically, are you ready? This is
Yep.
why pressure? That's it. That's all of this is like why pressure? Okay, and explaining why you get pressure at all is actually quite hard. Okay, so what is the structure of an explain answer?
Key fact, consequence.
Perfect. Key fact, consequence. Right. So can you see the structure of this question? They have just asked you to give them four of the five assumptions. Do you think that one of those assumptions at least might be the key fact here?
Yes.
Can you see how they've kind of gone, think about this, now do this?
Yeah, that makes sense.
Which of those assumptions do you think might be the thing here? The starting point, the key fact upon which our pressure explanation hangs?
Would it be random motion?
Yes, it is. Okay, so my key fact is the particles of gas are moving randomly. So that is a key fact, isn't it? Right now, we've got to explain the increase in pressure. Another key fact, equation for pressure.
Force over area.
Good. Where's the force come from?
Uh, oh, the random movement of it when they hit each other and they hit the wall of the container.
It's hitting the wall of the container that matters, isn't it? Because it's actually
Yeah.
hitting the pressure gauge matters.
Oh, pressure gauge. Yeah.
Yeah. Okay. Right now, can you see that before we get to P is F over A, we've got to go to F. Why do we get a
Yeah.
force? Okay, so can you see that's the next key fact, isn't it? Or the consequence of the first key fact. It becomes the next key fact. Um, so we've got because they're moving randomly, what happens next? The particles collide with the walls of the container, don't they?
Yeah.
And they bounce off. And when they bounce off, their momentum changes. And F is equal to rate of change of momentum, isn't it?
Yeah.
So can you see this is kinetic theory?
Yeah.
Can you remember going through kinetic theory and how you derive that PV is a third nm
Oh, that
c
was a long one.
squared?
Yeah.
Yeah, that derivation. And on the steps were the assumptions, and then the particles colliding with the wall, and the change in momentum of the particle. And then you had to add in all the other particles, and you had to include the time taken to go from one wall back to the same wall again, have a second collision, and all of that jazz, right? But there's a force on the particle, has to be to get it to change momentum. And so there's an equal and opposite force on the wall. And if you divide by the area of the wall, you get the pressure
Yeah.
on the wall, right? Can you see? So the particles collide with the walls of the container and their momentum changes. So there's a force on the particle. So there's a force on the particle. And then Newton's third law says there's an equal and opposite force on the wall.
Yeah.
And Newton 3 says there's an equal and opposite force on the wall. Okay, and then pressure is force over area. So the gas particles exert a pressure I mean, contributions added together. Right, now we still haven't explained why the pressure increases when the temperature goes up. So what we've got to do is we've got to modify this explanation of pressure to why the pressure goes up. So when the particles of gas are moving, what happens to them when the temperature goes up?
The kinetic energy increases as well with the temperature.
Yeah, so the
So
speed
they
of
move
particles.
faster.
Yeah. So the particles of gas, they're moving randomly, and when it gets hotter, they move faster. Okay.
Yep.
And as the gas warms up, the average velocity increases. Okay, they collide with the walls of the container and their momentum change is bigger. So there's a bigger, can you see, force on the particle and a bigger force on the wall, which means that the pressure increases. Can you see how we actually have to put that in? Because otherwise we haven't
Yeah,
explained why the pressure increase is expected.
yeah,
Now, I recognise that this is actually way more than a 2 mark explain.
true.
I think it's 2 marks. But actually explaining pressure is, I mean, it used to be a 5 mark question, and now you're lucky if you get two for it.